In this video, we're going to introduce what is a very important probability distribution known as the binomial distribution. And we're going to look at this introduction to the binomial distribution by means of a tool that we used at GCSE, namely tree diagrams. So, Pauline throws a normal fair cubical die 4 times. Let x denote the number of sixes she obtains in these 4 throws. Obtain the probability distribution for x. So for a 4 throw problem, we could illustrate the different possible outcomes using a tree diagram. And we're using a key at this stage that S stands for Pauline obtaining a 6. And F stands for a failure. In other words, she doesn't get a 6. We know that the probability she gets a 6 will be 1/6, and the probability that she doesn't get a 6 will be 5/6. So we can add the probabilities to the tree diagram very easily, and we get a diagram looking like that as our completed tree diagram. Now, the random variable x can take the values 0, 1, 2, 3 and 4. If we start off with what the probability of obtaining 4 sixes is, to get 4 sixes we must have a 6 on the first go, a 6 on the second go, a 6 on the third go and a 6 on the fourth go, and that's the only way we can get the 4 sixes. So the probability that we're going to get x equals 4 is going to be 1/6 times 1/6 times 1/6 times 1/6, or 1/6 to the power 4. If we look at the diagram, there are 4 different ways in which we can get 3 sixes. We can go 6, 6, 6, fail, 6, 6, fail, 6, 6, fail, 6, 6, or fail 6, 6, 6. So we've got 4 ways of doing it. Now the probability for the first route, 6, 6, 6, fail, is 1/6 times 1/6 times 1/6 times 5/6. And that is also going to be the probability for each of those other routes. So we can say that the probability that Pauline obtains 3 sixes is going to be a 6 times a 6 times a 6 times 5/6 times by 4. In other words, we've got 4 times a 6th cubed times 5/6. If we now move to the ways in which Pauline can get 2 sixes, well, the first one that will come, if we go up the tree diagram as far as we possibly can, will be a 6, 6, followed by failure, failure. But then we could also go 6, failure, 6, failure, or 6, failure, failure, 6, or failure, 6, 6, failure, or failure, 6, failure, 6, or failure, failure, 6, 6. So we can see there are 6 different routes of obtaining 2 sixes. The probability of the first of those 6 ways is going 1/6 times 1/6 times 5/6 times 5/6. All the different routes will have exactly the same probability. So we've got the probability that x equals 2. It's 1/6 times 1/6 times 5/6 times 5/6 times 6 because of the 6 different ways. So that's 6 times the 6 squared times 5/6 squared. Now moving on to the cases where we get 1/6. The first case that we come down reading down the tree diagram is 6, not a 6, not a 6, not a 6, which has got a probability of 1/6 times 5/6 cubed, And we can see that there are 4 different ways of doing that. So our expression for the probability that x equals 1 is going to be 1/6 times by 5/6 times 5/6 times 5/6 times by 4, or 4 lots of 1/6 times 5/6 cubed. There's only one way of getting no 6's. So the probability that x equals 0 is 5/6 times 5/6 times 5/6 times 5/6, or 5/6 to the power 4. So we've got all of the separate results, and we can summarise those as a probability distribution table. So the probability distribution for x is given in the table below. Now at this stage, we've got that distribution for the number of 6's obtained when Pauline throws a fair cubical dice 4 times, and we achieved that through the tree diagram. What about this problem though? Michael's got a biased cubical dice which has probability 0.3 of landing on a 6. He throws the dice 4 times, let y denote the number of 6's he obtains, obtain the probability distribution for y. Well, the only thing that's going to change here is the probability of getting a 6 is now 0.3. So that's the probability of getting a success, if you like. And the probability of not getting a 6 is now 0.7 rather than being 5/6. So the distribution for y is very, very similar to the distribution for x. So the probability that y equals 0 is going to be the probability that we get 4 failures on the trot. So that's going to be 0.7 times 0.7 times 0.7 times 0.7. So it's 0.7 to the 4. The probability that we get just 1 success is going to be 4 times by the probability of a success times by the probability of getting 3 failures. So that's going to be 4 times by 0.3 times by 0.7 to the power 3. The probability that we get 2 successes is going to be 6 times the probability of success squared, so that's going to be 6 times by 0.3 squared, times by the probability of 2 failures, which is 0.7 squared. So altogether we've got 6 times by 0.3 squared, times by 0.7 squared. For 3 successes, we're going to have 4 times by 0.3 cubed, times by 0.7. And for 4 successes, it's going to just have to be success, 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 which is going to have a probability of 0.3 to the power 4. When Peter and Hayley play a game, which must result in a win for one of the players, Peter has probability P of winning the game. They decide to play a series of 4 games, and it can be assumed the result of each game is independent of the results of the other games. Let Z denote the number of games won by Peter. Obtain the probability distribution of Z. Well, this really is almost exactly the same as before. If we were to draw a tree diagram, we could have success being Peter wins, failure being Hayley wins. The probability of success is P. The probability of a failure is 1 minus P. And if we just think of it like that, we can make use of the previous work to write down the probability distribution of Z. So the probability of Z equals 0 is the probability that Peter loses all the games. So that's going to be 1 minus P times 1 minus P times 1 minus P times 1 minus P, or 1 minus P to the 4. Probability that Peter wins just one game is going to be the 4 times the probability of a success, P, times by the probability of a failure, cubed. So that's going to be 4 times P times 1 minus P cubed. Probability that Peter wins 2 games is going to be 6 times by the probability of a win squared times by the probability of a failure squared. So that's going to be 6 times p squared times 1 minus p squared. Probability Peter wins 3 games is going to be 4 times the probability of a success cubed times by the probability of a failure. So that's going to be 4 times by p cubed times by 1 minus p. And finally, the probability that Peter wins all 4 games is just going to be the probability of a success raised to the power 4. So that's going to be p to the power 4. Now at this stage, I would like you to just pause the video and see whether you can do some similar work on the problems on this page. When you've done that, start the video again, and there's just 2 more problems extending the same technique again, and these are on the next page. So moving on to the next page, we've just got these 2 problems, which instead of being, if you like, a 2-stage tree diagram, involve a 3-stage tree diagram. So answer these 2 questions, and once you have answered these 2 questions, you can start the video again, and you will find that we've reached the end.